Thanks for joining, everybody. So here we are, the end of our first week of the intro course to data science from Lambda School. And even though we haven't had much time, these hour lessons are really short, as we've discussed. We've covered a lot of ground. And in the spirit of covering even more and not wasting too much time up front, I'm just going to pass it off right now to Ryan Herr, who will be talking more about statistics, sort of just picking it up from where I left off yesterday. So thank you, Ryan. And the one other thing I'll say, if you have questions, ask them in Slack, PMs, or whoever else will help you as appropriate. Thank you.
Thanks, Aaron. Hi, everybody. I'm Ryan Herr, data science instructor at Lambda School, and I'm super excited to continue with statistics. Last night we did descriptive statistics. Tonight we'll get into inferential statistics. So that's what we'll learn. I want to ask you, how should we learn? So let's do a poll. Let me try this here. Does Polly work in the?
It's just /poll, so no Y.
Oh.
I'll paste it real quick. I got that.
Yes, exactly. So anyways, there's nothing like messed up timing to ruin your punchline. But the idea here is, I'm curious whether you'd like to learn statistics with or without the agonizing pain. And you guys are gluttons for punishment. Some of you. I agree with the mentality of no pain, no gain. But we will actually, let me share my screen here. And I think tonight we will go with the without the agonizing pain. At least I'll do my best. That'll be my attempt. So please let me know if you can't see my screen. But here's again some more detail about what we'll cover, and it includes some terms that might sound scary. Null hypothesis significance testing. That will be at the core. But other concepts that you may have heard of before, standard deviation, and some other things that you may not have. This, what is a z-score, confidence intervals. Well, I'd like to approach this without the agonizing pain, with a computational approach, really continuing the approach that Aaron used last night, where we were using for loops and random number generators to simulate dice rolling and things of that nature. We'll continue that on and show that how that can fit in this framework of even null hypothesis significance testing, of what that is. This concept of statistics without the agonizing pain, this helped me when I was struggling early in my data science journey with some imposter syndrome. Have you ever heard of that? It's this idea that, like, okay, I'm trying so hard to learn this stuff, and it seems like I just can't keep up with everybody else around me. It seems like they all know what's going on and I don't. And so 4 years ago, when I was early in my data science journey, and I was coming stronger on the code side, had a little bit more background there, and I was a little bit weaker relatively with the applied mathematics and statistics. And so I thought, can I learn this, or am I just a pretender? And some of you maybe can relate to that if you maybe don't have as much statistics background, and that's okay. You can learn this. I was able to attend a great talk at a conference where a data scientist named John Rouser said, if you can program a computer, you have superpowers that can help you learn statistics with a feeling of joy, and not from a position of fear and self-doubt. So we'll see. It's a tall ambition. We'll see how we do. So I'll start by importing a couple libraries, our iconic trio, as Ryan Allred introduced earlier this week, and also a couple libraries from Python standard library. So last night you rolled your own mean function Tonight we'll use the ready-made one, and we'll continue on with the random number generation. So just one topic that we'll need to continue on with in descriptive statistics before we dive into the inferential, meaning to make inferences, to gain insights, and maybe even make predictions from the data. But first, this one concept that we did not get to address yet, and that is standard deviation. It's another way of describing values. Because we oftentimes use the mean or the average to describe some numbers, and oftentimes that can be a good description, maybe even all by itself. So have kind of a contrived example here, but say I bought a bag of a half dozen apples, and here in my list structure here, those are the weights of the apples. So if I calculate the mean here, we find out, okay, they're each half a pound, and that is really a good single number to describe these apples. They don't vary that much. But suppose I also have some pumpkins, and those can be more diverse. They could vary. So just again, a contrived example, but suppose I've got a garden, I'm growing pumpkins. One day I harvest a couple pumpkins. I harvest 3 decorative pumpkins like you could put on your windowsill that are 1 pound each. And then I harvest a couple pumpkins that are 3 pounds each, and you could bake yourself a pie. And then one of those enormous Atlantic giant pumpkins, which I am told can reach almost 600 pounds. So if I were to calculate the mean of these pumpkins, it works out to exactly 100, as contrived math problems often work out to neat answers. But you know what? It would be misleading. It would be deceptive to say the average pumpkin in my garden is 100 pounds. Really, we can't summarize these pumpkin weights with a single number. We can do better if we use 2 numbers. And so that other number is the standard deviation. If mean is a measure of central tendency, and median and mode are also measures of central tendency, standard deviation is a measure of spread. How far does the data maybe spread out either towards or away from that central tendency? So that's all that is. I'm actually not super concerned with the calculation right now. I just want to show that as we would intuitively expect, the apples have a low standard deviation, and this is in the same units as the original. So you can say, well, it's the apples weigh half a pound, but they can vary by 1/10 of a pound or 2/10 of a pound or so. But then the pumpkins, they have a much higher standard deviation. So we see right from that number a greater variance. So with standard deviation out of the way, now I want to get into what I hope will be a fun problem here. Clumsy Carl. We're going to try to settle a debate here. We're going to try to evaluate or test a hypothesis. So here's the scenario. Imagine a restaurant employs 5 dishwashers. They're conveniently, their first initials are A, B, C, D, and E. Alice, Bob, Carl, Dave, and Eric. They're breaking a lot of dishes over in that restaurant. One week they break 5 dishes, and Carl breaks 4 out of the 5. So his coworkers, they have a hypothesis. Their hypothesis is that Carl is clumsy, so he earns that alliterative nickname. But Carl protests, "No, I'm not clumsy. It's just bad luck. It's just random chance. It could have happened to anybody." So either Carl is clumsy, it's his fault, he's being careless with his handling of the dishes, or maybe it was just bad luck. Carl's idea that it could be bad luck, we can call this the null hypothesis. And we can try to say, what's the odds of the hypothesis being true by considering the opposite? well, what if the opposite was true? How likely or unlikely would that be? It's a little bit like in math. If you ever did proofs, where sometimes to prove something in math, you say, in order to prove this thing is true, I want to suppose for a minute, what if it was false? And then show that that leads to some sort of contradiction, something that's impossible. In this scenario with probability and statistics, it won't come out to be literally impossible, but instead it will come out to say, well, maybe it's very improbable that something could have happened randomly by chance. And so there are some ways of evaluating that probability. Do some math to help answer this argument. What's the probability it was just bad luck? So similarly to what we did last night, we can write a Monte Carlo simulation, which, as Aaron explained, it sounds kind of like a hotel name or something like that, but it just really, in our case, involves for loops and random number generation, as we promised at the beginning of this lesson. So we're going to write a Monte Carlo simulation to estimate the probability that Carl breaks at least 4 of the 5 dishes, assuming that breaking the dishes really is a random event, as Carl is claiming. We're going to assume that the dishwashers have identical workloads and skills. So the idea is, okay, if we find out that the probability is small, then we're going to say, okay, sorry, Carl, it's more likely that you're clumsy. So I want to show you the full thing first, and then we could maybe dive into step by step if it requires some more explanation. But I'm going to write this loop here. This is the test that we say, okay, we're going to make a random choice. We're supposing that this is a random process of who, when a dish gets broken, who might have broken it. So we're going to make a random choice from among our dishwashers. We're going to loop do that 5 times. And then we're going to count up the number of times it was Carl and return that value. And so that's our test. And if we repeat that a whole bunch of times, like maybe 100,000 times here, then we can plot a histogram of what those tests look like. So here's the histogram. And again, I will back up and explain the code more if there's some desire for that. So under the null hypothesis, the mean number of dishes broken by Carl, we see as it is in the graph. If it really is random, then on average, Carl's going to break 1. And you could see how that's intuitive, right? If you've got 5 dishwashers, 5 broken dishes, if it really was random, you'd expect everybody to break 1. But it can vary. Standard deviation suggests it's about plus or minus 1. So you might say you'd expect everybody to break 0 to 2 out of 5. But you may not expect someone to break 4. That didn't happen too often. And there's some ways that we can quantify how frequent or infrequent that was. So we have this thing that we promised in the beginning, the Z-score. It's also called the standard score. And it's actually not as intimidating or complicated as it might sound from the name, the Z-score. It's just this idea to say, how far away were you from the mean? And then compare that to the standard deviation. So in this case, okay, if Carl broke 4, the mean is 1. So he was 3 away. The standard deviation is about 1, so that doesn't really change it. And so we find out that, okay, he was over 3 standard deviations from the mean. So that's what Z-scores mean. And the useful thing there is that because Z-scores are all in the same units of standard deviations, you can compare across experiments or across scenarios or situations with the Z-score. And so sometimes that can be nice, but in this case, settling this debate, I'm really more interested in still thinking not so abstractly in dimensions of standard deviations from the mean, but just really more concretely around the problem. And I like to think back to the probability that we promised before. So, okay, if we did this test, this random test, 100,000 times, then how often was it out of those 100,000 tests that Carl broke 4 or more? And so we say 656, so it can happen, but if we look at a percentage, it happens an awfully low percent of the time. It happens less than 1% of the time. And we could simply, if we're taking the sum and then dividing it by the number of tests, then that's the same as taking the mean. And this value that we've calculated here, that is a p-value. You've maybe heard of p-values before. You may have less confidence about how to explain it. And if you feel unconfident on how to explain a p-value, you are not alone. There was a great article by 538, the website for quantitative analysis of politics and sports and culture. They did this story about how not even scientists, and particularly even scientists that were at a conference that was about like meta research about how to do research and communicate research. Not even these scientists can easily explain p-values. And the challenge is, even if you have a grasp on the technical definition, it's hard to translate it into something intuitive and easy to understand. But that technical definition is, okay, what is the probability of getting results at least as extreme as the one you observed, given that the null hypothesis is correct? So in this case, concretely, what is the probability of getting at least as extreme 4 more broken dishes by Carl, if given that the null hypothesis is correct, given the idea that this is really random, that he's not clumsy. And unfortunately for Carl and his argument, the probability, it's possible, but it's not probable. This p-value is 0.007, about in that ballpark. And so we're going to actually reject the null hypothesis. There is a convention that's somewhat arbitrary, to be completely honest. Somewhat arbitrary convention to say that the threshold for p-values that many publications use is 0.05 or 5%. So if the probability of the null hypothesis of getting a result at least that extreme, if the null hypothesis is correct, if that probability is less than 5%, then you're going to reject the null hypothesis, and you're going to say that sorry, Carl, we're going to side with your friends here who are giving you a hard time, who gave you the nickname Clumsy Carl. Is just really unlikely that it was bad luck and random chance. You must be careless or clumsy in some way. It is possible to, Aaron's also covered the ability to have complex list comprehensions, other statements in Python. So, it might be a little bit too clever. You could do this as a one-liner, but you might be better off having some named variables and putting something in a function and breaking it up into some smaller parts like this. And even this, if it's your first time looking at something like this, might not be completely clear. So I'm going to take a look at how I'm doing on time and do another poll, if that's okay, to say, want me to explain the test function step by step. Okay, sorry. I guess that it would probably be a yes. It is hard to be all things to all people. So if you're an experienced coder, then maybe this is review for you. But this could also be a meta lesson, and to say, how do you, if you look at a snippet of somebody else's code, and you're not exactly sure how it works, how can you get a better understanding? And to me, I love this concept of the Jupyter Notebook, or environments that use a notebook like Colab, where it's this concept of the REPL that we've talked about. And so you can just start putting pieces of this in the REPL step by step. So I can say, okay, I've got these dishwashers. I maybe don't want to type it all out, so I'm just going to use their first initials. So now I've got these dishwashers. That's a list of people. And now I'm going to see how this random choice thing, just to make sure that I understand how that works. So if I do this random choice, okay, it's gonna give me one of them back. And if I do it over and over again, it's going to give me a different random one. Okay. So now if I put this in the list comprehension, then just make sure that I understand that. Okay, so I'm getting the 5 as I expected. And then now there's this other thing. There was this count command that we used, right? So there was this idea like, okay, now we have our test, the list of the 5 breakers, but now there's this method in Python on a list that if I do count the number of C's, it's going to tell me, as I expect, okay, there's 1 C here. And so it gives me a count of 1. If I were to regenerate this, and then now run it again, it's going to give me a 0 and so on. So I see that, like, okay, by hand, I'm simulating some of these trials. And if I did that over and over again, many times, such as 100,000 times, then I'm going to get, well, let me just see what I get if I use a smaller number. I think that oftentimes if you're dealing with huge loops, it can be helpful to say, well, let me break it down into a smaller quantity that I can actually observe all the output, right? Okay, so here are all my Carl counts. And now if I could do a histogram on this, and it's going to be less of a shape. But if I started to increase the number of tests, it's going to start to get more of that shape that we would expect. And I can start to say, okay, now this idea, maybe why don't I go back to 10 tests so I can see them all. And so now I can see this idea of like, okay, we're checking this part of the loop where we're saying, okay, checking on for each test, was it greater than or equal to breaking 4? And we saw in these 10, it never was. So if I do a sum of this expression here, then I'm going to expect to get 0. If I did it again, let's see if we try to get at least one that has a 4 in it. I guess this is proving the point that you can wait a while, right? So this even gives you, practically speaking, a little more of the intuition that, yeah, it really is quite rare. So we won't bother with that anymore. But the idea here is, if you're trying to understand somebody's code, break it down piece by piece, maybe line by line, or maybe even parts of a line. If I have this list comprehension, I can break up even pieces of this in the REPL, and this can help me to understand. It's sort of like the site Python tutor.com, I believe it is, where you can visualize the flow of a program, and you can see what are the values of the variable at any given point in time, almost like if you were looking at an Excel spreadsheet and you're seeing the values of your data at all times. Well, programming in a REPL like Jupyter Notebook or Google Colab's notebook environment can give you some of those same computer programming superpowers if you take the time to leverage them. So there's no magic here, and there's no shortcuts. So for people who wanted to learn the hard way, well, this is part of what that could mean as well. It depends on your perspective on whether it's the hard way or the easy way, but it's putting in the effort to experiment and tinker until you understand. In the interest of time, I'll keep on moving on, and just very briefly explore thought experiment of how we could have done this clumsy Carl and the broken dishes problem. How could we have done it without using our computer programming superpowers of the for loops and the random number generation? So one way, of course, is if you had a 5-sided die. Don't know if they even make those, but that would be convenient in this problem. If you had that and a whole lot of patience to do what we did, I don't know if you really realize it, but just in a fraction of a second, 500,000 rolls of the 5-sided die, so to speak. So you could do it that way, or you could do it with combinatorial probability. And since this is a relatively simple contrived problem, it's possible. And to many people, actually, this way might be easier. It just depends, personal preference. But if you get into more complex problems, it may become more difficult to enumerate all the possibilities. So the way that would work, if you've done anything like this in school, or maybe you haven't, but think about, okay, what are all the ways you could get 4 C's? Well, there are 4 different ways if the non-C is in that position, and there's 4 different ways if it's in that position, and so on. There's 5 different positions it could be in. So there's 4 times 5 or 20 different ways you could get 4 C's. Then there's one way, by definition, to get 5 C's. And then there's 5 to the 5th total possibilities. So if somebody and we get indeed the same value, or very close to the same value, let's actually go up and check. It'd be worth a moment. I wouldn't expect it to be identical, but we have 0.006 here, 0.006 here. So some of these digits way out here. And it's going to be a little bit different every time. This is an estimate of the probability and the Monte Carlo simulation. The fact that you have randomness means it's different every time, not as a bug, but as a feature. So speaking of bugs, the next example is going to actually be very, very similar to Clumsy Carl and the broken dishes. But this time looking at actual data from a real world experiment. Are beer drinkers more attractive to mosquitoes? And maybe that sounds kind of funny, but it actually has real world implications. Mosquitoes can carry malaria, and so there are public health implications. And I would be curious, I'm not going to switch over to Slack since I'm a little bit clunky here on the Zoom and the Slack and the polls, but I'd be curious if somebody does want to throw a poll in there. Who thinks beer drinkers are more attractive to mosquitoes or not? So there was a research study that was done about this. They set up this intricate system of tunnels and traps to where somebody who is drinking either beer or water can be by one of the traps, and the mosquitoes can smell the person and go towards the person or towards empty air. They ran this experiment. They had volunteers who drank either beer or water, trapped and counted the mosquitoes. So here's some data in Python list form for the number of mosquitoes that were collected in the traps for each of the volunteers, each of the beer volunteers, each of the water drinking volunteers. We can inspect the length of those lists to confirm what the research abstract says, that there were 25 volunteers who drank beer and 18 who drank water. We can compute also the average number of mosquitoes in each group, as well as the standard deviation, since we learned about that. So in the beer group, this was the average number of mosquitoes attracted. And the water, it was over 4 less. So there were the average person who drank beer attracted 4.4 more mosquitoes than the average water drinker. So now the question is, it's a statistical question. It's a null hypothesis significance testing question. Is this difference, this effect size of 4.4, is that sufficient evidence to claim that drinking beer makes you more attractive to mosquitoes? And you can imagine some legitimate arguments on either side. On one hand, it's yes, that there's this difference here. On the other hand, the standard deviation, you would expect that the number of mosquitoes attracted did just vary. I don't know, randomly or on some other factors that weren't measured. But the participants were randomly assigned to these groups. So that there are some variations here. So maybe that difference, that apparent effect, was just due to random chance, or maybe not. What's the probability? Well, if we want to evaluate the claim that drinking beer makes you more attracted to mosquitoes, if that's the hypothesis, that's the effect we observed, let's consider the null hypothesis, the idea that it happened just by chance. Now we can't write a function to simulate the flight path and decision-making properties of a mosquito in the same way that we can simulate randomly assigning dishes to be broken, or coins to be flipping, or dice to be rolled. But we can do something that actually is conceptually similar. And this was the amazing thing to me in that statistics without the agonizing pain talk that John Rausser gave. He used this example. He didn't show the code, so I figured out the code for the example and sharing it now with you, paying it forward. But he did show conceptually how you could do this instead of with complicated statistical formulas, using for loops and random number generation. And the procedure is called a permutation test, or if that sounds too fancy, you can just call it shuffling. So the idea is, if the null hypothesis is correct, then these labels, these groupings about beer or water, they have absolutely no meaning. They carry no information. It was just coincidence that this person drank beer and this person drank water. But really, people are people. The drink didn't make a difference. So let's just combine this group together and then randomly shuffle them into two groups that could be the same size. So we can say, okay, well, we'll use Python's split notation or slice notation, array slice notation, to say we're going to take, after we randomly shuffle these beer drinker and water drinkers together, their data, so we don't know who is who, we've shuffled them all up randomly, and now we're just going to take the first 25 and put them in group 1, and then everybody else, and we're going to put them in group 2, and then we're going to compare the means. How is group 1 different than group 2? We can repeat that many times, so this is still the same sort of setup that we had like in the Clumsy Carl example, but now we're doing real-world research. And we can take a look at a histogram of how those tests turned out. And we'll plot here this effect size that we observed. We'll plot this as a vertical line, a black vertical line here. And so here's what the distribution looks like under the null hypothesis. So if this was just random luck, how improbable would that be to get an effect size at least that extreme? Well, it's out there on the tail. If beer versus water really doesn't make a difference, if it was random, then you would expect that on average, the two groups would have no difference, right? That's intuitive here, that this is centered around 0 and that we see a number very close to 0 here for the mean under the null hypothesis. But then this bigger question was, well, what's the spread? What sort of deviation could we expect away from that, and does it deviate enough that maybe it's possible to get an effect like 4.4 more mosquitoes just by random chance, right? Well, it turns out that's actually very similar to the Clumsy Carl example. That observed effect size, 4.4 more mosquitoes attracted by beer drinkers, that's over 3 standard deviations from the mean under the null hypothesis. That's the z-score, also called the standard score. And here's the p-value. Again, the probability of getting results is at least that extreme. So if you assume that the null hypothesis is correct. So again, we have a very low p-value, meaning a very low probability of seeing a result that extreme if this was random. So we reject the null hypothesis. It's under that 0.05 threshold, well below it, and that's what the researchers found as well in this study, which I've linked to here. That yes, there was individual volunteer variation, but despite that, beer consumption consistently increased attractiveness to mosquitoes. These results suggest that, hey, this is a risk factor for malaria that we should be considering when we make public health policy prescriptions. So this was one way without having to use any formulas and lookup tables or advanced statistical conceptual knowledge, to just use for loops and random numbers to do some null hypothesis significance testing and find that p-value. There are other ways to do it. We could do it instead of computationally with the permutation test. We could do it analytically using a t-test. There are libraries in Python that implement this. When we calculate this, we get very similar p-value here, 0.0004, 0.00037, same thing. But the complicated thing is, well, there are these parameters that you have to put in for the t-test function. So even if somebody's already implemented the function for you, you still have to know how to use it. So I wouldn't fault somebody if they're more comfortable with this than with this. But personally, for me, coming more from a coder hacker sort of background, this statistics for hackers type of approach is what resonates with me. But whatever works best for you, that's your prerogative. So coming towards the conclusion of this lesson here with one final example, and then we will put you into the assignment where you will have an opportunity to practice some of these skills. So the last thing that we'll look at is this concept of a confidence interval. So if before we were trying to estimate what's the probability that that this effect is real, well, now the confidence interval is related, but it's a slightly different twist. It's an answer. It helps to answer the question, how precise is my estimate of the effect size? Not just binary whether or not there was a difference, but like how much difference, and what's my uncertainty around that size of the effect. For example, in this case with the mosquitoes, like you'd wonder if I reran this exact same experiment, the exact same procedures, how much would the effect size perhaps differ? Would we see the same thing if we ran that experiment again? So I'm going to show you first how it's implemented in another library. This is and let me zoom out so we can see the full visualization here. So this is a Python visualization library called Seaborn. I believe that we have mentioned it perhaps already this week. That is really useful for some statistical visualizations, including it has built in this idea of adding 95% confidence intervals to bar plots, so that if we're wanting to summarize in one bar here in one number the mosquitoes per beer drinker on average, well, this length of the bar, that's the exact mean that we computed, but this black line here is, you can think of it as an error bar or a 95% confidence interval to say we have some confidence that the mean is probably somewhere along this black line. Like if I had to give you just one number, I'm going to tell you it's right here on the blue vertical line here, the length of this bar. That's the average. But if I could give you a range that reflected my uncertainty of what that quantity really is, then I would say I'm gonna estimate that the average number of mosquitoes per beer drinker is going to lay somewhere on this black line. And similarly for the water drinkers, saying if I had to give you one exact number, then I would say is this number right here. But really, there's some uncertainty because it's not like we tested every person in the city or the country or the world. That would be impossible. Statistics is about sampling a population and then potentially making inferences that may apply to the rest of the population, but with some uncertainty or variability, right? Because it may depend on the people who you happen to sample. So this idea here of how we could figure out these numbers that the Seaborn visualization library is giving to us for free, so to speak, batteries included. The idea is to use a concept called bootstrap resampling. That's how these are calculated. And it is drawing samples with replacement. And I think that to explain what that means, the best thing to do is first just show you some examples, and you'll be able to see. So there is a function in the Python standard library for making random choices with replacement. And if I just basically rename this function bootstrap sample, I can take a look here. First of all, here's my actual data. And I've, just for convenience, just to see the order of the data, I've sorted it. But this was the original data. This is from the experiment. This was the data that was collected for the water drinkers. And then here was the mean number of mosquitoes that were attracted by the water drinkers, right? But if we do a bootstrap resample and then calculate the mean, it will be slightly different, very similar, but slightly different. So this idea is it's resampling with replacement. So imagine you're reaching into a bag to pull a marble out, and you're recording the color of the marble or whatever, and then you put it back in. So you could actually pull that one out again. You might be wondering, why would you want to do that? Well, the idea here is a statistic of central tendency like the mean. It could be influenced by some outliers that you may or may not have included. Think back to the pumpkin example. If you including that huge, enormous pumpkin, one of those changes your mean dramatically versus leaving it out. And so if you're not exactly sure what is the ratio in the pumpkin patch of these little pumpkins versus the huge ones, then you have some uncertainty about what the true average is. and you can approximate that or quantify that by doing a bootstrap sample. So sometimes you're going to get more outliers on either direction in here, and sometimes you won't. If I do another bootstrap sample and take the mean again, then this time I get slightly different set of values and slightly different mean. If I do that over and over again, then, and I think that I meant to have a histogram in here, so I'll add that real quick. And a little tip here, if this semicolon, when you're working with Matplotlib visualizations in a notebook environment, sometimes it will give you this extra stuff here, where this is actually what is being returned by Matplotlib's histogram function. If you want to suppress that and just see the plot, one sort of hacky tip is to put that semicolon in there, and it will repress any of the other Matplotlib output and just show you the visualizations. So even if the confidence interval piece, even if you don't retain this, maybe you'll retain the semicolon trick. So hey, so we see here this this estimate of the effect size here. If I did over and over a bootstrap sample of the beer drinkers and a bootstrap sample of the water drinkers, and then I compared the means, then we say here is the variation that we could expect. This is not under the null hypothesis. This is assuming that we do have the distributions correct. And now the 95% confidence piece is to say we're gonna sort of to cut off either end of this bell curve. We're gonna cut off the most extreme 2.5% here, and we're gonna cut off the most extreme 2.5% on this side, and we're left with the 95% in the middle, and say what's that range? And in this case, with the mosquitoes being attracted to the beer drinkers, we're saying that 95% confidence interval ranges from 2 more mosquitoes being attracted by the beer drinkers to almost 7 more mosquitoes being attracted by the beer drinkers. So again, it's different ways of quantifying your uncertainty. So the p-value was saying, what's the probability that this effect was real at all, that there's a difference between the beer drinkers and the water drinkers? And that p-value was what enabled us to with some confidence say, yes, we believe that this apparent effect is real, and that the mosquitoes really are more attracted to the beer drinkers. But by how much? Is it exactly 4.4 more mosquitoes? Well, probably not exactly that amount. There's some uncertainty there, and a way of quantifying this uncertainty is to say, well, it might be 2 to 7 more mosquitoes that are attracted by the beer drinkers. That's a way of quantifying that uncertainty, giving it a range. You can imagine if this 95% confidence interval, if it crossed 0, if it ranged from positive to negative, then that means that you really don't have confidence that the effect existed at all, right? If you said, well, it's somewhere between -10 and 10, it's like, well, then you actually really don't know. But it's a good sign and consistent with our earlier null hypothesis significance testing that that this does not cross 0, that it remains positive. You can say it's 2 to 7 more mosquitoes. So that is inferential statistics, several topics in inferential statistics. I'll scroll back up. Sorry for the aggressive scrolling there, but just to recap what we covered here. So, because the assignments, we'll get back into this as well. So final topic in descriptive statistics, we talked about the standard deviation to measure the spread of a variable, or a spread of some values of data, and how that measure of the spread can be combined with the measure of a central tendency, like a mean, median, or mode, to describe some data. And then we apply these concepts to now inferential statistics, making some inferences or drawing some insights from data, with an emphasis on the null hypothesis significance testing, also getting into z-scores, also called standard scores, and confidence intervals. We attempted to do this with for loops and random number generators, and attempted to do it without agonizing pain. Now, how well we delivered on that, could be in the eye of the beholder. I think that maybe the pain started out pretty bearable, and maybe by the time we got to confidence intervals, well, it's getting late, and we've hit about an hour. But I'm so excited to share this material with you, not only the what, but the how, because as I shared in the beginning, this did help me to overcome some of those feelings of imposter syndrome, some of those feelings of like, you know what, I just don't know if this is going to click for me the way it seems to be clicking for everybody else, right? Sometimes it can take repetition. So if it didn't click for you today, don't worry. That's probably on me, the way my explanation. But you know what? Sometimes, as I mentioned, it just takes repetition. So I would encourage you again, if you'll pardon the scrolling. But down to the bottom, I have lots of great links that you can check out. After the lesson, to reinforce some of these concepts, and even some of them, as I mentioned, using some of the same examples. So this video, only 12 minutes long, I really think it's fantastic, and you can go as deep as you want to go. This could keep a aspiring data scientist very busy for a long time, and it's very applicable in the real world. Because null hypothesis significance testing is often used in a business scenario for A/B testing. This idea that we have a business that has some sort of a website, has a mobile application, could even be used in a brick and mortar context, where you want to try some experiment to maybe acquire more customers or retain more customers, and you want to say, did this difference make a difference? I changed something on my website. Did it help me convert more prospects into customers? Well, what if I have the majority of my customers still go with the old site that we think works pretty well, but what if we randomly assign some of the visitors to this new experience on our website or mobile app and see if it converts any better, has better results? And then these techniques, whether you're using this type of approach, or maybe if you've heard of something called Bayesian statistics, that could be used as well for evaluating A/B testing. But somehow you're going to have to do some inferential statistics to evaluate the A/B test. And even broader than A/B test, this really comes up when you do the type of data science work that is really about analysis, and sometimes it's called type A data science work, in contrast with type B data science work, which is the B is for build. So some roles, some projects will gravitate more towards this type A analysis, where it is maybe diving into the data to do descriptive statistics and visualizations, and inferential statistics as well, like we've covered tonight. Other data science work might look a lot more like just software engineering and building things. And the lines are very blurry between the two. And to me, that is not a bug, that's a feature, because I could get bored if I got pigeonholed to doing just one thing. So if you're attracted to a blend of types of work, then this profession, this career that you're considering here in this intro course may be for you, because there are a lot of opportunities to have a blend of experiences, and it will be good to understand this content if you want to have those type of experiences that include that type A analysis. If you, on the other hand, lean more one way or the other, then just know that about yourself, as you learn on your data science journey, which we hope will be with us in Lambda School, but wherever you go and however you learn about the types of things that you like doing within data science, because it's a big, broad field, and the way that you like doing it, and then seek out projects and positions that align to those interests. And I hope that might include doing some inferential statistics with a computational approach. So thank you so much for hanging with this lesson tonight. We are about at an hour, and I'd like to now give you the opportunity to dive into assignment and then the group discussion with the PMs. I have not been able to, I apologize, to keep up with questions. So if there are, Aaron, are there questions that I should?
There have been a few that I think have been addressed. Quinn just asked something, though. I thought that normal had to mean that the area under the furthest left percentile had to equal the area under the furthest right percentile. Shouldn't these two numbers be equal? And so those two numbers, they are about a normal distribution, but they reflect different things. Does anybody know what the first number represents versus the second number? Bonus points if you can remember the Greek from yesterday. Yep, the first number is mu, the mean, the center. That's the main thing we've been focusing on. The second number is sigma, or what you actually learned a little bit more about today, right? The standard deviation, the spread. Exactly. Now, there are slight distinctions between these terms, but for now, it's okay to just sort of bucket them all together as the center and the spread. Any other questions, though? And sorry for stealing that one.
No, perfect. What I found as well, that the deeper you go in, especially if you can be like with thanks to the internet, you can be a sort of a fly on the wall as like statisticians start to argue with each other.
I gave a complete wrong answer, though.
What's that?
I gave the wrong answer because he said normal distribution. I assumed it was characterizing a normal. It was an interval. It was a low and a high. Sorry for interrupting, but I got that. Thank you for catching that, Joanne.
Okay. So this screenshot here, yeah. So so in the 95% confidence interval with this procedure, it wouldn't have to. It doesn't have to be symmetric. The distribution doesn't necessarily have to be normal. I'm not sure if that's getting any more toward what you're after.
I mean, we'd have to go back to see what the mean is in this case, but the mean probably is about halfway between 2.15 and 6.72.
Yeah, and you can see, honestly, actually, this is looks pretty close to normal. There are statistical tests that you could do to see how close a distribution is to normal, but yeah, these numbers intuitively make sense that you've got 4.5 plus or minus 2.5. So that's symmetrical in that sense, and that it doesn't cross zero. That would be a bad sign given what we talked about before.
Mm-hmm. Anyway, I'm sorry for interrupting you, but
no.
Everybody makes mistakes. Thank you for correcting that, Joanne.
Yeah, the percentile function isn't returning areas. You could, it's really the same as, so like think about like the median is the 50th percentile. So if you were calculating median, it's just saying what is the single value that is halfway through that data. So instead of saying the median that is 50% through the data, then you're saying like, okay, if I sorted all my data, I'm just going to say go 2.5% of the way through the data and give me that value, which is going to be almost the, it's going to be not the minimum, but it's going to be one of the lowest values. There's only going to be 2.5% of values in in the data that are lower than that. And then on the other end, you're going to go 97.5% of the way through your sorted data and say, give me this value that is going to be one of the highest values, not the maximum, but closer to the maximum.
It's a good question. Good discussion, though. And hey, it's good to remember about mu and sigma anyway, right?
Yeah, absolutely.
I'll pretend I meant to teach that now. Any other questions? We should let you get to the homework, and I'll let Ryan describe it for a sec. The one announcement I have before that, though, so next Monday is a holiday in the United States, at least, Labor Day, and so it's a holiday. So we will not run on Monday next week. We will run Tuesday through Friday. So there's no class tomorrow because normally we don't do intro course on Fridays. And then there's no class on the weekend, but there's no class Monday either. So it's 4 days without class, and then coming back for another 4 days with us, with class, Tuesday through Friday. So please do come back. I mean, please take some time in that weekend to enjoy and relax and recharge. Of course, you can definitely keep looking at the assignments if you have a little bit of time to do that, and that's a great thing to do bit by bit. And you can ask questions in Slack, and people will respond as they see it. But the next class is Tuesday next week. That is the announcement, just to emphasize that. Everything else is the same, 5 to 8 Pacific. All right. Thank you.
All right. So the assignment, which I can share if it hasn't been already in the Slack, is this notebook here, so we're going to go back to the Titanic data set and calculate some summary statistics. I encourage you actually to do something that I didn't show in the lecture, but is real world for data science, as we've all discussed, looking up documentation. So using the describe function in pandas, which would be most commonly how you're calculating summary statistics, is using pandas or NumPy. So you're going to look at summary statistics for age and fare, plot some histograms, just kind of think about what you notice about the shape of the distributions, what you notice about their spread, just a sentence or two that you can discuss in the group. Then I'm encouraging you to redo the clumsy Carl problem, but suppose he broke 2 of the 5 dishes instead of 4 of the 5 dishes. And I'm encouraging you, this is not a mandate, but do look at the lecture notebook. It probably would be too difficult of a problem to do if you didn't look at it, but don't copy paste from it, in which case that would make it a trivially easy problem. Instead, go through the time. You've got the time, even if it seems a little bit silly, of typing it out for yourself, because then you will internalize it more. It's not so much about getting it literally in your fingers, but it's more about the act of typing it out with your fingers gets it into your head, so you're not just reading, but you're also writing, and you're internalizing it, and you really did have this experience of doing it. And I don't need you to type out these names. That would be too tedious. But if you want to type out the rest, then that's my suggestion for this one. Then returning to something similar to the work that you did with Aaron last night. But simulate the distribution of adding 2 dice. So you've got 2 dice, you roll both of them, you add them together. So if you rolled 2 6s, you got a 12, and you're saying, okay, well, if you did that over and over again, then what's the mean roll that you're going to get? What's the mean sum? What's the standard deviation? Calculate that standard score. And then think about here the probability of rolling a 10 or higher. So it's, again, using that sort of test function type of setup if you want to do it that way. And last, applying this 95% confidence interval concept to our apples and pumpkins. And I'm not looking for you to rewrite these functions. That would be too much work in the time allotted. So it's more applying these functions to that data to calculate that how much confidence you have around the mean apple weight and the mean pumpkin weight. Make sense?
Great. Everybody ready to go? And remember, PM's in a little bit less than an hour, and that's a really great opportunity to talk, work through these things as a group, ask questions live. And it's part of how we do things here at Lambda School. We're giving you that experience. All right. Thanks, everybody. Have the video up shortly.